All right. Let's, I don't like that chair in front of me. Can you remember to tell me I've got an umbrella here? Okay. All right. Oh, good. They've set the camera so you can see me moving a chair. All right. Hello, everyone. Welcome back to week 8 and more linked lists. And hopefully no more tech issues from now. So let's just hope. Anyway, we've still got out your week 10 practice exam, so there might be some tech issues there, but hopefully not. All right, so let's do more linked lists. So on Monday we went back to the previous week and we talked about linked lists. We redid linked lists. We inserted into a linked list at the head, at the tail, and we created some code that is actually letting us build up our linked list. And we did that code without a single function after we redid it, which makes that code quite difficult to understand. And there is a lot of repetition in the code as well. So I thought that today we're going to do a few things. Today we're going to make a few functions and move that, structure that code with functions a little bit. And then we're going to insert anywhere in the linked list, because so far we've only gone at the very tail or at the very head. And you should really be able to insert anywhere you want in the linked list as well. So we're going to look at that. And then after the break, after the halfway break, then we will look at deleting nodes and freeing all the relevant memory. I noticed there were some very good questions on the forum about freeing memory and kind of causing memory leaks, but then also cleaning up memory leaks. So we will talk a little bit about that as well, because that's what it's all about. That's why we're learning C. Okay, so let's get started. Okay, so in our piece of code that we wrote that is just all straight down one in main, it looked quite messy as well, because we have here, we're creating a new node, and then we are printing that new node, printing the linked list, and then we're creating a new node again, and then we're printing it again. So some of those things are really just calling out to be a functions. We really want to clean that up. Otherwise, every time you create a new node, you'll just have the same piece of code, which is really the very definition of why we would want a function there. So let's create a function. Let's do one for printing at first. Okay, so let's do a quick function that will print out a linked list. Sophia? You got a smiley face there? Yeah, yeah. Okay, so what will be... What do we think for a function that will print out a linked list? What do you think we need to give that function to be able to traverse a linked list and to print out every single node in a linked list? What do we think we need to give it? Pardon? Yeah, so we need to give it the head of the list, so the first location. And then after that, if you've got the first location, you've got every location by definition of what a linked list is, because I've given Sophia some very small Easter eggs today, so it's going to be really challenging her to throw them in any way whatsoever. But once we have the head of the list, we really have, every single node in the list, because each node will reveal the address of the subsequent node and the subsequent node until it gets to null. So all we need to give it is the head of the list. And what is going to be the output of a function that prints out a linked list? Yeah. Nothing. Well done, because you're just going to print it out. So it's going to be a void. Okay, excellent. So our function is void. I guess we can call it print list. Why not? And we're giving it an address of the head of the list. Okay, and then we really want to take this piece of code and we want to move it out. Yeah.
If we are using null, then we can actually return an array from a function.
So
you can return the pointer to there.
yeah, yeah. But an array by definition is a decaying pointer. So when you pass it, so it's like it decays down to, it's not a true pointer, but the name of the array and also the first element of the array, they have the same address. I don't know if Andrew did that piece of code that it will give you, if you print out the address of just the name, if you print out the address of the 0th element of an array, it's at the same address. So when you pass an array to a function, you're passing the address of the 0th of the first thing.
Okay, so if an array is stored in the heap and you have a pointer to the array or a pointer to the 0th element.
Yeah, so if you've dynamically allocated an array, then you can return.
Yeah, because you're returning the pointer to the 0th element, and in this case, the 0th element actually points to some memory that still exists. Unlike if you were to declare it within a function.
Yeah.
Just normal array declaration that it would point to like now unallocated space.
But it depends again if you've allocated that memory inside a function that you then left, because if you've left that function gone. Yeah. It depends what you're trying to do. Not in 1511. Yeah. Okay, so we'll have a current, so we'll have a pointer called current, and we're going to take that pointer to point to the head of the list, which is what was passed to this function. And then we're going to traverse through the array, so we're going to go through, not array, sorry, linked list. We're going to go whilst current is not equal to null, which is signals that we're at the end of a linked list, and we're going to print out each of the nodes in that linked list. So now everywhere where we are, I'm going to call that function that we have done, and then we will check that it's working. So let's do that. Where else do we do it? We did it over here as well. So let's call the function from here as well. And then let's also not forget to do a function prototype at the top. Okay, so now let's save it and compile it. Okay, so what have I done? I've clearly used current somewhere else. I've used current everywhere. I've used it here, so that's what the issue is. You've always got to do a bit of fixing after you start moving things out to functions. Okay, so let's run it, see that it's still working. Yep, so the print list function is now working. Okay, so now let's move out, making a new node out into a function as well, because we've now done it twice, so we're repeating the code twice, so it will be a lot faster to build up our list by just calling a function each time. Okay, so let's do a function. Okay, so for a function that will create a new node, what do I need to give it? Come on, I know it's week 8. Yeah. Sorry? So I need to give it what to put into that node. So I need to give it the data and the address of the next thing. Okay, and what would be the output of it? What should I return if I've created a new node? What do I want to return to my main function? Yeah, I just want to give it where that node is. So I want to return the pointer to that node that I've just created. Oh, great throw, Sophia. I wonder how small I can get the chocolates to challenge you. Okay, so my output is struct node, and I'm going to call it create node. And then what will I give it? I'm giving it the data, and I'm giving it, oh my gosh, an address. Okay, so let's do that. Okay, let's now actually make the function. Okay, so now let's take this piece of code that we did here and move it out. Okay, so in this new function then, what am I doing? I am creating a new node, mallocing some memory for it. I'm giving it some data. That should not be, that should just be data. And the next will be my address that I passed to it here. And then I'm going to return that new node, the address to the new node that I've just created. Okay, and we'll run through the code, so don't worry. Let's now actually... So here, instead of calling malloc, I can now call my new function create node, and I'm going to give it some data, and the data was 5 and null. And that will create and put the node inside the address will be head. Okay, so now if I want to create a new node, I'll just keep calling my function. Okay, so the first node that I've created is going to have the value 5, and it's going to have a null in it. And then afterwards, I'll print it out, and then we can see what else I need to do. Okay, let me save that. Let's compile it. I forgot to prototype. Okay, let's try that again. This is why you write functions straight away. Now I've got all these references to all these lovely things that I have no idea what they are. Okay, there's a new node being created here, so I'll just call my create node again. Okay, so I'll create my new node and then, okay, let's try that. And then we'll run through the code. Okay, so now I've got a node that's got a 5 in it, so it's printed it out, which was this first thing. And then I've gone to the end and I've inserted the number 9 into it, so the new list that it will print out will be 5 and 9. Okay, so how is everyone feeling? You want me to run through it line by line and draw it out? Yep, let's do it. Okay, so, and let me just tidy up. So what I've done also is I've actually created a bit of white space here because I think it's maybe more clear if I draw it on white space. Okay, let's do it. Okay, so we've got our main function. We've created a pointer to head, which means that my variables, this is my main running now. And inside my main, I've got a pointer to head. So it's going to be a pointer called head. It's got no value yet. And then what I do is I say head is going to be equal to, I'm going to call the function create node and give it 5 and null. So what that means is I'm going to head down to my function create node over here. And if you remember, I've given it the values 5 and null, which means that what happens is this is equal to 5, and this over here is equal to null. Okay, so what happens here is I go to line 48, and I create a pointer to a new node. So I've got a pointer with a new node being created, and what I assign to it is some dynamic memory. So I'm actually calling the function malloc, which is getting some memory and allocating it the size of my struct node, which means that it's creating somewhere in my memory a node, and it's of size struct node, which means it's going to have space for a point of data, and it's going to have a space for a pointer to the next struct node. So it's going to be empty, that's created, and what I've returned is, let's say, for example, this is sitting at 0x000. What malloc will return to that new node is that address. So now I have an address for that new node. On line 49, I will assign my new node, and this is my new node that was created. So into this new node, into the data member, which is this one here, I will assign it whatever data was given, which is 5. So on line 49, I'll put 5 inside my new node, and on line 50, I will assign whatever was inside this next, which is the one that was coming from here. It's null, which means I'm assigning null to my new node next member. And then what I'm doing is I'm returning new node into my, look at that, I've made a mistake. My new node was inside my create node function. So that over here should be moved. Great. Okay, so what I've done is inside my create node, so actually this new node address is going to be inside my function here. This pointer was in here. Oh, it just changed colors by itself. Why did it do that? Nothing can ever go smoothly. Welcome to tech. Okay, and then I return new node to the place where I called it from, which means that the address of that new node is going to come in here and going to be returned over here where it says head is equal to. So when I've called this create node function with 5 and null, I will actually get the result of that, and the result of that, which is what we're returning, the result of that is 0. So the result, oh my God. I'm done here, I'm done. Why does it hate me so much? There we go, okay. So the result of this create node is 0x000, which means that now it's being assigned into head. So head is now going to be equal to 0x00, which is this new node that I created inside my function. Okay, then on line 23, I'm going to go to a function called printList, and I'm going to give it the head, which means that I'm giving it the address 0x000. Okay, so then I will move down into my printList function, which is the function over here. And I've given it 0x00. So this address here is 0x000. Okay, so now I'm sitting inside my print list function. And inside this print list, I'm going to create a new pointer. It is called current. And this pointer is going to be assigned the address that is head, which is this head over here that I've passed to it, which means it's going to have the address 0x000. And then I go into a loop, okay? Shh. I know linked lists are very exciting. I'm also very excited by linked lists, but let's just a bit of shh. Thank you. Okay, so then whilst current is not equal to null, so I check my condition. So is my current, which actually has an address, is it equal to null? No, it's not, because there's an address assigned to current. Current is actually 0x00. So it's not equal to null. I'm going to go inside this while loop. I'm going to print out whatever is sitting inside my current data, which is going to be this 5 here. And then I'm going to say current is equal to current next, which means that I'm going to go to the right-hand side, look inside what's sitting inside current next, and that's null. And I'm going to say that my current is now equal to the next thing, which is equal to null. I'll go back out and check the condition of this, which is now null. So is null not equal to null? Well, that's no longer holding true, which means I'm not going to go into this while loop. And now I'm going to come out of that while loop, and then I finish this function here. Okay, so what that means is that all of this is now gone. It's cleaned it up. And now I go back to my main. Okay, so now as I go back to my main where I called that print list function from, done. I'll move on to my next line of code. And my next line of code is saying struct node current is equal to head, which means that inside my main I'm creating a pointer to current, and I'm assigning the value of head to it. And the value of head right now is 0x000. So that means my current is equal to that as well, and that means that this is now my current node as well. Okay, then I'll go through here, I'll check the condition. Is current next, so accessing the member of current next, and that's equal to null. So is null not equal to null? Well, that condition is not true, which means I don't go into this while loop and I exit straight away out of it. Okay, and that means that if I exit this loop, that means that this current next is going to be equal to null, which means that I'm standing at the last node of my linked list. So then I move on here and I create a new node. Why not? So inside my main, I create another pointer to a new node, and I call a function create node with 9 and null. So I'll go down to the function, my create node function over here, and I've given it 9 and null, which means that this function is now going with values that were given to it, so 9 and null over here. And what it's doing is it's now creating a new node. Okay, great. And that new node is going to be equal to whatever the address is of this. So I'm going to malloc some memory, which means what I'll do is I'll create another struct node, and that means it's going to have some data. It's going to have a pointer to the next. And let's say, for example, the address is 0x111. And that means my new node is now equals to 0x111 over here. Then I'll take that new node, I'll go inside the data member and assign whatever was here, which means I'm assigning 9 to it. And over here, I'll access the next, and I'll assign whatever was given it on the next, which is null. Excellent. And then what I'll do is I'll return the new node. So I'm going to return that address back up to my main. So if I head back into my main where I called it from, which was over here, what I'm doing now is this new node over here that I've created is now equals to this address that I've given back to it. So 0x111 is now what's sitting here. And now to connect these two nodes up, what I've done is I'm accessing my current next, and current next is over here. This is now my new node over here, the address of it. So my current next, which is over here, is now going to get the address of new node, which is 0x111. And that means instead of null, this over here is now going to have 0x111. And that means that it's now going to be pointing to this, and that's going to be pointing to null. And then I'll go back down and print the list out again by giving it the head of the list. And the head of the list is still 0x000. We haven't changed anything, which means that this is the head of the list right now, so it's going in the right direction. Okay, Tom, can you do a little poll if that all makes sense? And if we're ready to move along to insert anywhere in the linked list? How is everyone, well, no one ever answers in the theatre, but how is everyone feeling in the theatre? Yes! Yay! Yes! Good! Woohoo! We've got a linked list. It's got 2 elements in it. This is the smallest linked list ever known to mankind. Okay, let me just then throw in a few more nodes into this linked list so we have something to play with. And then we're going to talk about how to insert anywhere in the linked list and all the conditions that you must consider. There we go. Okay. All right, so how would we now, let's say I want to create a few more nodes at the end. Okay. Now this is going to call for itself to be moving to a new function as well. If I want to insert at the end of this list and I want to insert some more things at the end of this list, I really want to kind of have this as a function which allows me to get to the end of this linked list. So I really just feel like adding at the head at this point in time so we can move on. 12:30? Okay, yeah, I think so. Okay, so we've got something at the head, we've got something at the tail. Or maybe we'll just go at the tail, it makes more sense at the tail. You're just nodding at everything I say. Yeah, okay, good. All right, how's that poll going? Good, great, excellent. Okay, so let's add a few more nodes in to the end of the list and then we'll insert, actually, you know what, we've got 2 nodes. Why don't we insert something in the middle of those 2 nodes? So right now, our linked list looks something like this. We've got something that has a 5 and the address, and let's say these are made up addresses, okay? That's not what the computer has assigned to it, Malik. So that one's pointing to 0x111, and it's going in here, and this is pointing to null. So right now, that's what my linked list looks like. Not a lot happening, but let's say I would like to insert something over here in the middle of the linked list. Okay? So what do you think would be some strategies that we're going to adopt, perhaps? And there's a few ways you can traverse through. Find the middle of the list, perhaps, or I love just looking at people and then everyone's awkward. Just throw some chocolates around. Why not? It's 12:30. It's lunchtime. The throwing is amazing. Oh, that was, I spoke too fast. Oh. Hey? Are we going to learn? I can't hear you. I'm so sorry. Oh, complexity. No, we're not going to learn complexity in 1511. You will learn it in the next course, yeah. But I'm trying to talk a bit about everything we do in computing is really for efficiency, but not ready for efficiency yet. She's going to kill everyone in this theatre today. I feel like the people at the back are feeling a bit hard done by. You did? These are easy to throw, okay. Okay. All right, so a few ways we can do it. Let's do it by doing it kind of in a similar way that you're perhaps doing it in the assignment. Oh, the camera's doing some weird pans. It's trying to capture Sophia, I reckon, throwing the chocolates to make you all feel like you're a part of it. Sorry you can't get any Easter eggs through the screen. Someone's asked what's going to happen to Monday's lecture. Nothing. You get a day to relax and to dream about linked lists as opposed to write them, and to do your assignment as well. So let's do, for example, let's do inserting into a linked list by, this is going to get ugly, by finding the middle of it. Okay. So the first thing I really want to know then is what the size is of my linked list. Let's write a function that calculates the size of a linked list. How does that sound? Everyone sounds really excited about it. So I'm just going to go with it.
Counter variable, yeah.
So I'm going to make the function called size linked list, and then we'll talk about what I'm going to give it. Okay, and let's do this function. Returns, oh no, I shouldn't say returns because that's giving away the output. This function calculates the size of a linked list? I don't know what it returns. It's a surprise. Okay, what would be the input of a function that needs to traverse a linked list to find out the size of it? Yeah. I love that. That's like your reply. Every 10 minutes, every function I write, you just say the head. Okay, so the input is going to be the head of the list, because once we know the head, we know everything. And what will be the output of a function that, yes, the size of the linked list, which means it's going to be an int. Okay, so let's do, okay, so, oh, I thought in the chat you were talking about Easter Monday lecture. You were talking about our other Monday lecture that was so good. Okay, so the output is going to be an int, and my function is called something ridiculous, size linked list, and I'm giving it the head of the list so that I can actually calculate out. Thank you. I've got an official shusha. Excellent. I feel like everyone gets overexcited in these lectures. Okay, so size of a linked, hey? Linked lists are so cool. You know what? Linked lists are actually really, really cool. So, yeah. Okay, so let's do size of a linked list. So what do we need to do in this function that will calculate the size of a linked list? What do we reckon? How do we count this linked list up, the nodes of the linked list? Yeah. Yep, I'm just going to have a counter, and then I'm going to use that counter to count everything up, okay? So I'm going to get a struct node current so that I, just for good practice, I don't move around. So I know where I'm currently located. I'm going to assign the head to it, which means I'm at the beginning of the linked list, and then I'm going to traverse through that linked list, hey? Thank you. So counter right now not initialized, so I'm going to initialize it to 0. And then we're going to have a look at what that does to us. Because is the first, yep, no, we're going to see what it does, okay. Okay, so struct node current is equal to head. I'm going to have a while condition. And what do you reckon? Will I keep going through the whole linked list until I get to null? Or will I stop at the last element of a linked list? You want to stop at the last element? Okay, if we stop at the last element, that means that we're going to go until current next is not equal to null. And we'll see what happens. Okay, and each time we're going to add 1 to the counter, and then we're going to move along. I'm just counting how many things there are. Indeed, I do, because otherwise I was just going to show it as it happens, yes. So if we go and stop at the last node, okay, my list right now is 2, and if I compile it, and I should probably give this the head of the list. Okay, so if I go compile it again, okay, great. We'll get there, we'll get there. Here we go, prototype. Okay, and now we've got okay. All right, so now let's run it. What should size return to us when I've got 2 nodes here? What should it return? What do we want it to return to us? 2, okay? Now it's going to return 1 to us because we are stopping at the last node, which means it's not counting it. So what we want to be going here until is we want to go past the end of the linked list so that we are counting every single node in here. So if we save it now and run it again, then now the size of the linked list is 2. Okay, so now we've traversed the linked list and we've got the size of it, which is just so exciting. I bet you're all, yes, look at that. Someone is just as excited about the size of a linked list. Okay, and then what should we do now if we want to insert in the middle? Just for fun.
3 points is slow and fast.
That will go down really well. I feel that Paul will just like break out of the YouTube. All right, so I'm going to calculate the middle of the linked list by doing something amazing. I'm going to halve the counter, and then I'm going to insert after that halfway point, okay? So, and this is like super inefficient what we're doing right now, okay? So don't think that this is like super efficient coding, but it's good at the beginning of your coding journey to write things line by line so that it really makes sense. And then as you get better, you will start to cut out lines and start to find shortcuts and stuff. Okay, so my midpoint is going to be size divided by 2, let's say. So right now in my current terribly short linked list, which has 2 elements in it, what that means is this midpoint is going to be equal to 2 divided by 2, which is going to be 1. Okay, fantastic. So what I want to do now is I want to insert a new node in after the first node has occurred of this linked list. Okay, so that means I need to traverse through my linked list and I need to be able to insert at the point that I want. Okay, we've got 2 options. We can either make a function or we can just do it inside our main. What do we want to do to start with? How is everyone feeling? Thank you. But you're just one person. Yeah. Function straight away? I think we should do a function straight away because, you know, once you start moving things out into functions, that's when you get the overwhelming amount of errors as well because there's always variables forgotten and sometimes it complicates things. Whereas when you do functions straight away, sometimes it almost allows you to write the code just by like saying what should happen. Okay, so let's say I'm going to have a function called insert middle, and I might give it something as well. Okay, if I have a function that inserts in the middle, okay, what do we think will be the input of this function, and what do you think will be the output? Okay, so the input will be the head and also the position that we're going to, and think about your trains as well. You might have some function in there that will get you to insert at a certain position. So I'm going to give it the head and the position that I want to insert in. And then what do you reckon will be the output of the function? Yeah. Oh, this is going to be, I can't hear. I can't hear, I'm so sorry. Yeah, thank you. So I might return to it. Well, my create node function returns a pointer to the new node. So if I insert into the middle of the list, then what should I be returning? Nothing. Yeah, that's right. So I could return nothing because my head hasn't changed. I don't have to worry about inserting at the head. Yeah.
But if there's a situation where it's an empty list, then you have to return the head.
Absolutely.
Or if you're not returning the head, then you can do similar to how they did in the labs this week, where you pass in a struct, and the struct contains a pointer to the head, or the struct contains the pointer to the head. So
this is all about, linked list is all about thinking about your boundary conditions. And the boundary conditions always occur at the head, at the tail, if the list is empty, for example, or if the element that you're looking for is not even inside the list, which we will talk about in a second, okay? So in the perfect world, and we have the perfect world because we have a linked list with 2 nodes in it, it seems, hey?
What a perfect world.
It is a perfect, this linked list. This is why you do computer science, to create a linked list with 2 nodes in it. So in this perfect example, okay, please, shh. My voice is loud, but I don't really want to yell. So in this perfect scenario, well, semi-perfect scenario, we've got a list that's got 2 nodes, which means that we have something in our linked list, so we will always be inserting in the middle. Everything is great, but then what happens if there is no head, and we will talk about that in a second. So let's do it for our perfect scenario first. Yeah?
The imperfection is that there's only one linked list. We should have more.
We should have multiple linked lists. We should have circular linked lists.
Yeah.
Doubles. A linked list and a linked list. We should... There are so many possibilities. Okay, so in this example to start with, okay, we're going to say that we're going to return nothing just to start with, and then we're going to create a situation where we might need to return something. Okay, so I'm going to give it the head, and I'm going to give it an int position. All right. And now we're inserting in the middle. I've given it the head, so I'm going to give it the head of the list. And then I'm going to give it the position, which in this case, I'm going to give it this midpoint situation here. And I'm not returning anything, so I don't need to assign anything here. I haven't actually said what node I wanted to do. I haven't created a node for it to insert, which is a bit of a worry. But that's OK. Let's just... create it. Where should we create the node? Where should we create the node? Let's do it in the main. Okay, I'm going to create the node to insert. And then I could pass it the node as well. There is many things we can do. Let me just do it here. Oh my gosh. I'm going to call my function here to create the node, and I'm going to create the node number 13, and then I'm going to insert, now I cannot call it in here, cancel that thought, because now I've got to pass it the node as well to insert. Okay, I'm going to create it over here. Okay, so I'm going to call a new node, I'm going to create that node. Talk to me.
So in this situation, it's a bit contrived that you're...
It's very contrived. Yes, it is very contrived right now. Yeah.
This might be applicable for like if you want to insert into a sorted list or something.
Yes, yes. It's...
Do we do sorting algorithms?
We unfortunately do not do sorting algorithms. We used to do them when the term was 12 weeks, and we don't do them anymore, but I am trying to bring them back. Yeah, enjoy. Okay, so struct new node. We've got a node that is, we're creating a node with 13 and null, and now we want to insert it in the middle of the list at position, whatever this position is here. Okay, so how will we know that we've gotten to this position? What do we think? Thoughts, ideas, suggestions? No? I guess you're all busy discussing it amongst yourselves. Okay. So what I'm going to do is I'm going to count up my nodes, and when I get to that midpoint position, then I'm going to insert into the linked list. Okay, so I need something that will count the nodes for me. Let's say I'm going to use a counter here, and then I want to move through my nodes. Okay, so the first thing I'm going to do is I'm going to create a current pointer that will point to the head. And that's what I'm going to use to pulse through, traverse through the list. Okay. Now, what do we reckon? We're going to go past the end of the list? Well, in this contrived example, doesn't really much matter. So, but let's go towards the end of the list to see if we can get to the halfway point. Okay.
Also put like and current is not equal to.
We will. Yeah.
Counter is not equal to position.
Yeah. Okay. So we're going to count up every time we hit a node. I'm going to increase this counter by 1. Okay. And then I'm going to move my pointer 1 along. So I'm going to move to the next node each time. All right. Fantastic. But over here, we really need to know when I come out of this while loop, I need to know what's going on. In this current situation, what this while loop will achieve is that when I exit the loop, my while condition is going to mean that current is equal to null, okay? Which is not going to be great for me because I'm not going to be able to insert anything because I'm going to be at the end of the list and I'm going to have absolutely no idea where I was in the list or where I should insert, okay? So one way to check for this is also to check the condition that my counter is not equal to the position where I chose to insert into the list.
Isn't there, so we started, or rather, is there a mismatch between how we started counting position and how we're counting count? Because I like intuitively something tells me that, you know, starting counting from 0.
Yes, yes.
It might be
So,
not at the middle point,
absolutely.
but past the middle point.
Exactly. So we're so used to starting at 0, but is the first node 1, is it 2? And you can just run the code, see what happens, whether you're 1 short, 1 long, and then see where you're at. Okay, so let's try this. And in the chat, yes, you can do an if statement to check whether the counter is equal to the position instead, and then insert in if you want. So in my current situation, what's happened is when I exit the loop, either my current is equal to null, or my counter is equal to the position that I want to insert in. Okay.
Current is going to the next one. When the, yeah, it's going to go past it by 1. So you're not checking after count increases by 1, you're not checking.
Yeah. Okay, so if my current, no, not current, if my counter is equal to the position, then I'm going to insert this new node that I've created. Okay, so if I've created a new node, okay, so over here I've created this new node, and this new node is basically going to assign 13 and null to it. Now what I want to be doing is I want to take this node and I want to connect it to here, okay, and then I want to take this node and I want to connect it to here, okay, and I want to break up this connection basically. So what does that mean I need to have as my addresses and how should I change my position so that my new list is going to have my new node in the middle? So if I've gone past it, counter is equal to position, and we're going to see if it works or not. But what I want to be doing, that means, what do we reckon? Everyone's losing the plot. Yeah?
Current next should be your new node.
Yeah, so my current next should be my new node, okay? Assuming that my current is there, okay? So my current next is going to be my new node, which I've created. And what that means is that my current next is going to go in here. And then what should my new node next be? So my new node next is going to be, and this is where the mistake is going to happen. Exactly. 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 So I want to say that this node here should link up to whatever is in my current next. However, if I've written current next is equal to new node, I've already lost where on earth that is happening. So I really need to have my new node next as the first thing. So my new node next is going to be equal to whatever's inside current next, and that should go here. And my current next is now reassigned to the new node, wherever the new node is sitting. Okay, should we try it out? Let's try it out. And then we can run through it line by line, and then we'll take a little break, and then we might delete that node as well. Okay, so let's see where it's inserted it. Oh, how unfortunate. It didn't insert it in the right position. It's inserted it at the end of the list because my new node had the number 13 in it. So let's see what happened and why it did that, because it felt like everything was going so well. Okay, so let's have a look what's actually going on. Okay, so over here what I've done is I've used the function insert middle, and I've passed it the head of the list and a midpoint. Okay, so the head of the list was my first thing here, and my midpoint was equal to 1. So when I go to this function over here, okay, when I move to this function, what I've given it is the address of the head, which is 0x000, and the position which I've given it is 1. Okay, so on line 59, I've created this new node, which is this new node here, and I'm going to delete my arrows from it right now. So this is currently my new node, and it has the value 13 and null. I've then got a counter that's equal to 0. And then I've got a pointer to a current that's equal to the head, which is 0x000. Okay, so then I start my while condition, and my while condition is, and that means that my current is now sitting over here. It's pointing to the start of the list at 0x000. Okay. Okay, so condition here, current is 0x000. Is current equal to null? No, it's not. So this is true. And is counter not equal to position? My counter is currently 0. My position is 1. So that's also true, which means I go into this while loop. What I'm going to do is I'm going to increase counter by 1. So I've increased it by 1. And then I'm going to move my current to my current next, which means I'm going to take this address and move my current along to it. I'm going to now have this as the current. Okay, great. Then I'm going to go back here and I'm going to check again. Is my current not equal to null? Well, current is currently 0x111, and my counter is 1. So my counter is equal to the position, which means I'm going to come out of this while loop and I'm going to go in here. Now, if counter is equal to position, which it is, that means I'm now going to insert. So my new node next, which is this thing here, is going to go to current next. But my current next is actually my second node, not my first, which means that I'm going to have it as null. And I'm going to assign null into here. And then my current next, which is this node here, is going to get the address of the new node, which is my node over here. So it's going to get the address 0x222, which means it's now going to be pointing up to this node, and this node is now going to be pointing to null. So the situation has occurred potentially because we're counting wrong. We're counting our nodes up wrong. It could be fixed by starting your counter at 1. So saying that when I get to the first node, that's the node I'm at. It could be fixed in a different way as well. So let's just fix it in one way where we start this counter at 1 instead. And let's try and compile it again. And then run it again. And so now it's inserting it into the middle because now my current hasn't moved off that first node. Okay, so one of the best things you can do with linked lists is draw a diagram and go through it, because then you can see what on earth is happening. All right, I feel like everyone's angling for a little break. So let's have a 5-minute break and then we'll come back to delete from lists as well. Hey? I'm going to add to the list whilst the break is happening. I'm going to add to the list whilst the break is happening because the list is horrific. let's delete. Hey, let's delete. Yeah, yep. Okay, I've grown the list a little bit so that we have something to delete just by adding things at the head because it was the fastest way to do it. So I've now got a really kind of big list and that we can delete from anywhere. Because when we were inserting and we were doing the function for insert anywhere, we really missed out on a lot of boundary conditions that we did not discuss. So in the deleting, I would like to now talk more about those boundary conditions. What happens if the list is empty? What happens if something's happening at the head, something's happening at the tail? Because those are all the things that are going to make a big difference. In this current example, it's a very contrived example. There is always a middle. There is always something in the list. But what happens when that's not the case, which is, real life? We don't always have perfect situations. So those are the things that we always need to consider. And really, if you, in your assignments and in your labs, those are the auto tests that we run based on the boundary conditions. So what happens if the list is empty? What happens if we have to insert at the head? What happens if we have to insert at the tail? And so on and so forth. Okay, so I'm going to go to some diagrams to talk about deleting first to start with, and then we'll do the code. Shh. You're all very lively for week 8. I am very surprised. Usually week 8, everyone's half asleep. Okay. Let's go to deleting. I should have really done that at the beginning. Okay, so where can I delete in the linked list? If we have this lovely linked list, and right now, let's say my linked list, looks something like this. If it has, I'm just going to make up this linked list, so just bear with me. Let's say it's got 5 things in it, and it's got 13, 2, just making the numbers up now, 6, 7. Okay, let's say it looks something like this. Okay, so right now I can delete any of these nodes. I can delete this one, this one, this one, this one, or this one. So what that means is that I can delete at the head of the list. And if I delete the head of the list, what does that mean for me? Yeah, I need a new head because otherwise I've lost my linked list, okay? So deleting at the head is special because I need to change the head of the new list, okay? What happens if I delete at the tail of the list? What does that mean for me? There's no tail, okay? And then this one is just going to be pointing to null, okay? I can delete between any 2 nodes that exist. That's really the easy thing to do. And also, I can delete nowhere. And that if I have an empty list, there is nothing to delete from an empty list because it's empty already. Or perhaps what I was looking for doesn't exist. So let's say I want to delete a node that has the value 10 in it. And I'll traverse this linked list looking for a 10, but it's not in there, so I will not delete anything because that doesn't exist. Yeah? Well, it depends what the question is asking you. Usually in 1511, you will only ever be asked to delete the first instance. Because it's harder to delete every single instance potentially, depending what the question is. So it depends how hard the question gets. The easiest question will just ask you to, so like let's say the first few questions in the exam, they will only ask you to delete the first instance or to insert an instance. Shh. I feel like I'm putting a baby to sleep. Okay, not that any of you can really associate with that. Okay, so deleting when nowhere, if it's an empty list. Okay, I will check if the list is empty. So if my current is equal to null, for example, and the current is equal to the head of the list, which means that if the head is equal to null, there is nothing in this list. So all I'm going to return is null. I can also return head because head is currently null, so it doesn't really matter much. So that means I haven't deleted anything, okay? It's an empty list. I'm just returning a null, okay? What about if I'm deleting? What about if I'm deleting when there is only one item in the list, okay? So if my list is only composed of one thing, and that means that I'm going to delete that one thing, what does that mean is going to happen? So this is now the head of the list, it's the only node of the list. What happens if I delete it? Yeah, so I'm going to have, my head is now going to be null. I'm going to have nothing. So I free the head of the list. Okay, deleting when at the head of the list with other items in the list, okay? And that means we've kind of talked about it briefly. If I delete the head of the list when there's other things in it, that means I need a new head of the list, and it's usually going to be the next item after the head. So let's say I want to delete my head, my current head of the list, so the first thing, okay? So that means I'm going to delete the current node, which means I'm going to free the memory for it, which, you know, kills that node. That means what I have to do is I need to change this pointer to the head. It's going to now be pointing to the next item, whatever is sitting inside my current next, okay? So my new head is now going to be whatever was sitting inside this current next, and then I'm going to free the current node, which frees the head of the list. Okay, so it deletes that top thing that I want to delete. And now Siri's even pumped into the conversation, and she's not sure she understands. Well, too bad, Siri. Okay, what about deleting when we're in the middle of two nodes, okay? So for example, I'm looking for a certain data point, and I want to delete a node with 3 in it. All that noise it makes it really hard to hear online for those that are tuned in online. So please, 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 please keep the noise down, because the people online can't really hear that well. Okay, so if we're deleting in the middle of two nodes, which means perhaps we're deleting this one with data point 3, we're going to delete this node here. We need to traverse through the list until we find the node that we want to delete, okay? So we're going to loop through until we find this node here, and we're going to check whether or not it's equal to 3. Now, if I'm deleting this node with the number 3 on it, you'll see it's like it's getting hectic. Current next, next. Why am I searching for current next data? Why am I not just doing whatever's inside current data? What do you reckon? Yeah.
Because you need to work with the current change for the next one.
Exactly. So if I'm sitting at current data, if I'm sitting over here and I've matched, I know that I want to delete this node, I do not know what the node previous to it is, because it's a single linked list. It moves in one direction only, okay? And that means that if I'm standing over here, I don't know what came before it. I only know what comes after it, okay? So what that means is I need to always be checking one ahead of me so that I can keep track of where I am in this previous one. And we can also have a pointer called current that we keep at the head, and we keep it moving along. We can have a pointer to a previous node as well, and we can always keep it one back to keep track of where we're at. So different ways to do things as well. Okay, so if my current next data, which means that this situation here is whatever's inside my current next, if we access this address and the data, so if that's equal, I'm still, the current is over here, this is still the current next. What I'm going to do, if it's not equal to it, I'm going to move along, But when it is, that means that I've reached the point where I want to delete. So what I'm going to do now is I'm going to take this current and I'm going to point it around to whatever was inside my current next. So I'm going to point it to whatever address was in there, which means I'm going to draw this arrow to the pointer to the node afterwards, and then I'm ready to delete whatever was inside my free current in the current next. So I'm ready to delete this node. And so the new linked list would be just these two nodes here. Okay, so and then set the new current next. So I've really just drawn that point there to the new one. Okay, deleting when in the tail. Again, we need to traverse through the whole linked list to get to the end of the list, and then we can delete. Okay, so if I get to the very end of a linked list, yeah.
If you delete something without pointing to whatever is after that, does everything after the thing you deleted delete?
Well, the memory is still there if you malloc the memory. Unless you exit the function, it will clean it up for you. But I have no way to access it because I will never find it again. Well, I mean, in these contrived situations, I'll find it again, but not, yeah. Sorry? Well, if you are, I think what the student is asking, what happens if that just happens by accident? So what I'm saying, you'll lose it, but you should be freeing every single node. Good practice to, if you're deleting the whole linked list, you need to free every single node, okay? Yes, in our 1511 situations, we are writing very small pieces of code. You know, once it exits, it will clean up itself a little bit, and that's okay for us. But once you go out to industry, you will then forget to start freeing things, and we don't want that to happen. It's very bad practice to not free memory that you have requested. You always want to be freeing whatever you've malloced. It goes hand in hand, and that's good practice to do that because it's a big security vulnerability as well, to keep that chunk of memory. And in larger programs, it's a lot easier to lose track of where you are and what node has been freed or what piece of memory still exists and hasn't been freed. Okay, so in the tail, I'll traverse through, but what I need to do is, again, I need to be able to stop at the previous node, so not at the last node, but the second last node in the list. And that's because I'm going to delete the last node in the list. And I definitely don't want to go until null because that means I've gone all the way past the end of the linked list. So I'm going to go to the second last node, and then after that I'm just going to delete the tail, and then I'm going to point my current next to a null. So to say that that is now the end of my linked list. So in all of these instances, you're actually following a very similar structure of what to do when deleting a node. Draw a diagram, please, please, please draw lots and lots of diagrams, okay, because it makes it a lot more clear what needs to point to what and where you need to stop and what you actually need to do, because otherwise it's very easy to make mistakes. Yeah?
What happens if you do the last one, but you've only got like 1 or 2 elements in your list?
So,
Like deleting the tail, because you had to go current next.
yeah, so excellent. So you're going to dereference a null pointer if you don't have a current next. So that is a boundary conditions that we would check for before we start traversing the list. But that's an excellent point. Well done. Sophia? Okay, so to delete a node in the linked list, find the previous node to the one that's being deleted, change the next of the previous, free the node, just free all the nodes, and then think about the possible edge cases, and that was, one of them as well. All right, I think let's write some code. How do we feel about that? Okay, I have grown this linked list, and this linked list now looks like this: 1, 18, 11, 13, 7, 5, 9. Amazing, what a list. Okay, so I'm going to delete, what should I delete? Let's delete like a value. We'll start by deleting a value because that's probably the easiest one to do. Okay, I'm going to write a function straight away. So I'm going to do delete node, and then we're going to talk about it. I'm going to give it nothing to start with, okay? And we'll talk about it. Okay. Okay, so what do you think we need to give a function that will delete a node from a linked list?
And the value of the node it wants.
Okay, good. So we want to give it the head of the list, and we also want to give it the value that we want to delete. Well, the value of the node, or... Okay, and what do you think will be the output of that linked list? Yeah, the head. Why do you think it's going to be the head and not just nothing? Excellent. Exactly. So we're going to be returning the head because we might have deleted the head of the list. So we want to be returning a pointer from that function. Just in case we've deleted the head has now changed. Yeah.
In this week's labs, they have a different method of doing it. Instead of returning the head, they pass in a struct which contains the pointer to the head. Right? The head
Yeah.
value. Why do we do that?
There is many different things to do, different, what's the saying? Different courses for different horses? That's definitely not the saying, but what's the saying? It was something about horses, I swear it was. But there's different ways to do different things. And when you start moving along from 1511, usually a lot of our decisions are made based on efficiency of the code. But in 1511, we don't really care about efficiency as much. We're going to let you out of here with really bad habits into 1521 to be educated by Andrew. And 2521, that's right. Okay, so we're going to return the head, and we're going to do it just in case we have deleted the old head and we want a new head. Okay, so struct node, we're going to be returning. This function is called delete node. Oh my gosh. I've got it. Delete node. And we're going to give it the head of the list. And we're going to give it a value that we want to delete. Okay, so I'm going to give it the head. And let's say I'm going to give it a value. I'm going to go for the middle of the list, okay? I'm going to go for the perfect situation to start with. And then we're going to see what happens if it's not the perfect situation. Okay, great. And I'm going to be returning the head out of it. So I'm going to say head is equal to whatever is being returned out of it. Okay, excellent. Someone in the chat is asked, why is the delete node function a struct? It's not, I'm returning a pointer to a struct node. So I'm going to be returning a pointer to the head of the list, and that's a struct node pointer. And that's why it's got that output data type. Okay, let's delete the node. Okay, so what are we going to do? We're going to travel through this list, and we're going to find the previous node to the node that we want to delete. Okay, there are two ways to do it. I can have a pointer to the current, and I can have a pointer to a previous, or I can go full out insane and do current next, 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 current next, next, next. Next, next, next. You can have so many nexts, right? It's not really so, and that's very messy. It can get very messy. So what do we feel like doing? Do we feel like being messy, or do we feel like being a bit cleaner?
Let's do it the messy way so we can see why it's bad, and
Oh.
do it the better way.
Just as I started writing previous. We could just do the nice way to start with. Let's just do the nice way to start with. Okay, no, you should create a bad way, but I did it in the lecture notes. So you should be able to see that that's not ideal. So If my current pointer is pointing to the head of the list, so if I'm currently at the head of the list, what am I at previously to the head of the list? Null. Yes, exactly. I am nowhere. I am nowhere. So I am at null. Okay? So what that means is that, let's say my linked list is, now the linked list is too long, but we're just going to, okay, so I've got 1, 18, 11, 13, 7, 5, 9, and that's going to be my null. Okay? So what that means is I've just set this one to the head, and my previous is sitting over here. So that means this is the head, and this is also where my current is, right now at the first node. And my previous is over here, where there is nothing going on here. There's nothing pointing to anything. So I'm just sitting at the previous node. Okay, excellent. So now I'm ready to shuffle along and to try and find the point where I want to actually be deleting. Now, I've given it a value that I want to delete. That value is 13, which is somewhere in the middle, which means that I'm going to have 2 nodes circling on the outside of it. Okay? So let's see how we move along and then actually delete it out. Okay. Let's do it. Okay. Okay, some boundary cases, okay? Or should we just do the perfect case, then we should consider the boundary cases? Let's do boundary cases because I want you to always think about them, okay? Always just type it into your code before you start coding so that you don't forget it, okay? First boundary case, what happens if it's an empty list, okay? How do I check if it's an empty list? Yep. Okay, if my current is equal to null, that means my list is empty. Okay? And that means I can return the head again, which is equal to null, or I can return null. Doesn't much matter. Okay? Then my other situation, what happens if I'm deleting the head of the list? Okay, and that means I'm going to delete the head. Okay, so what do you think will be my condition inside the if statement? What do we reckon? If I'm deleting at the head, that means the very first thing, the data is going to match the value that I want to delete. How do I check for that? Yeah. So not quite current next because it's at the node that I am. It's at the head of the list and my current is at the head. Yeah, so in this condition, I'm really checking that my current data, if my current data is equal to this value that I want to delete, so whatever was sitting in the head of the list, then what I'm going to do is I'm going to change where my head is at. I want my head to point to the next node. How will I make it do that? What do we reckon? Current, yeah, current next. So it's whatever is sitting inside my current next. And even if that's null, it's still going to give me null there, which is fine, okay? Okay, great. So I've now pointed to the next thing. That's fantastic. But what happens now is that I still have that piece of memory. I haven't actually killed it. So I want to kill that memory. And to kill it, I'm going to, well, kill is very harsh. I'm really freeing it from enslavement in this program. So I'm going to free the current, and then I'm going to return the head of the list, which is what I changed over here. Okay? And now we're ready to kind of look at the perfect case. We'll do in a second. we haven't traversed out to the end of it yet. So that's why, yeah. So I'm just doing everything at the beginning to start with. Okay, great. We now need to traverse this list. We've taken care of an empty list, so we don't have to worry about that. We know that there is something there. So now we want to start traversing, okay? Okay, so we're going to go through the whole list. If we're going through the whole list, do we want to stop at current equals to null, or do we want to stop at the previous node? We want to be traversing the whole list when we look for our value that we may need to delete. Where do you think we need to go to? I've kind of said it, so we want to traverse the whole list, okay, which means that we want to go whilst current is not equal to null. And I'm going to include the other condition here as well, okay? Okay, and so if I want to be checking each time, because if I just check if current is not equal to null, what's going to happen is I'm going to move through the whole list. I'm never actually looking for anything that I want to delete. I'm just traversing the list for fun. So I'm going to keep checking whether my current data is not equal to data, okay? And the reason I can do that is because I'm also using that previous node. So I'm keeping track of what is happening previously, which means that I don't have to look for current next in this case. Okay, that means I want to, each time I want to move along in my list. So my current is equal to current next. But I also have this previous pointer. What do you think my previous pointer is going to be? What should I set it to? So I am moving along in my linked list, which means that if this is my current, then my previous is null. If I move my current to here, where do I want my previous to be? Current. Okay, excellent. So that means that I want my previous to be current and my current to be current next. So that means when I exit this loop, okay, when I exit this loop, either my current is equal to null, so I have reached the end of the list, or my current data is going to be equal to the value that I want to delete. So I'm ready for deletion, okay? So that means that the node that I'm standing on is the right node. That's the node that I want to get rid of, okay? So I'm going to check, okay? I'm going to check what is the condition, okay? If my current is equal to null, okay, so that's the first possibility when I exit this loop. That it means I didn't find it, okay? It means that I have nothing to delete because that value was not there. So I'm just going to return the head of the list. Don't worry, we'll go through it as well, okay? And the other possibility is that I have found it and the node that I'm standing on is equal to the value that I want to delete. So it's actually, I'm ready for deleting, okay? Now, if this node that I'm standing on is the node that I want to delete, okay, then what I want to be doing is I want to actually be deleting. So for example, the node is 13 that I want to delete, and that means what has happened is that my current is now over here, if this is a node I want to delete, and this is my previous over here. So if I want to delete this node, what I want to do is I want to link up my previous node to the one that comes after current. Yeah? So how will I do that? Yeah.
Previous is current, previous next and current next.
Yep.
Previous next is previous next.
Yep, okay. So that means my previous next, so what's sitting inside my previous next, I want to now skip my current node and I want to go to the next one afterwards. So my previous next is going to be equal to my current next, And finally, I would like to let that node free from my enslavement, which means I'm going to free it. So I'm going to free the current node. And then to finish off the final bit, I'm going to return the head of the list because I've said that I'm returning something from this function. Okay, let's see what happens when we compile it, and then we will run through it line by line as well. And I've forgotten to prototype. Okay, let's try this out. Beautiful, and let's run it. Now, I forgot to print it out to actually check that we've done something after deleting. So I'm going to call the print list function again. I'm going to give it the head, and that will print out what is going on for me. Okay, so the first time it does the list for me, the list is complete, 1, 18, 11, 13, 7, 5, 9. And afterwards, I have successfully deleted the 13. So that's amazing. All right, how are we all feeling? A few thumbs up, a few thumbs up. Any thumbs down, any thumbs to the like neutral? That's a weird neutral, a few neutral thumbs. Do we want to go through it line by line?
Yes.
Yep, okay, let's go through it line by line. I'm going to start from here. I've called delete node function. And my God, just creating random things now. There we go. Extend this out a bit. All right, let's do it. Okay, so I've called my delete node function, and I've given it the head of the list, okay? And the head of the list is this address over here. I'm going to give all of these nodes fake addresses so that it's more obvious where we're going at. Okay, so let's say this is 000, this is 111, this is 222, this is 333, this is 444. This is 555, and this is 666. It's quite fitting, isn't it? Okay, so let's do it. I go into my delete node function, and what I've given it is the head of the list. So I've given it the address 0x00. So inside my main function, I've got the head of the list, the pointer to it, and it's equal to 0x000. And I've also given it the value 13. Very exciting, I know. I do, I swear I do. This is what dreams are made of, linked lists. Okay, I'm inside my delete node function. And what I'm doing is I'm creating a variable. It is a pointer. The pointer is current. Let me just get rid of this. Nothing works. Whatever. Okay, so I've got my current, and the current is set to the head that I've given it, which means it's equal to 0x000. And then I'm also declaring another variable. It's going to be a pointer called previous, and that pointer is initialized to the value null. Okay, what that means in my diagram is that my current is over here because it's pointing to the head, and my previous is null because I haven't really done anything. I haven't moved through the list. Okay, I'm going to check in here. Is current equal to null? No, current has a value. That means it has at least one node in there. So I will not go into this if statement. I'll check the next thing. Is current data, so I'm currently sitting here, is the data inside this node, which is equal to 1, is it equal to the value that I'm trying to search for? Okay? No, it's not, which means that I'm not going to go into this if statement either. Okay? So I'm going to keep going. I'm going to reach over here now, and I'm going to run through my while loop now to now traverse through and search for this value, whether I have a node with that value. Okay? So whilst current is not equal to null, which is what stops us from going past the end of the linked list a lot further and dereferencing a null pointer, and checking that my current data, so whatever is sitting inside my current data right now, is not equal to the value. So the value is 13 in this case. My current data is equal to 1. They are not equal. And my current is not equal to null, which means I'm going to enter into the while loop. And I'm going to say, OK, previous is now equal to current. Okay? My current is 0x00. So instead of null, my previous is now 0x000. And my current is going to be equal to whatever is sitting inside current next. So whatever is sitting in here, which is going to be 0x111. So that's now going to change to 0x111. Okay? So those are my new values. And now I go back and I check my statement again inside my while loop. So my current has still got a value, so it's not equal to null. And over here, that means my current has shifted 1 along, because it's now my current is 0x, so current is over here. And previous has also shifted 1 along, so previous is now over here. So my current data is equal to 18. So I'm now checking that 18 is not equal to 13. That condition also holds true, which means I'm going to go inside this while loop, and I'm going to change my previous to the current. So my previous is going to be 0x111, and my current is going to be whatever is sitting inside my current next. So it's going to be 0x222 now. What that means is that those things have moved along in my diagram as well. This is now my current, and this is now my previous node. I go back and I check again, is current equal to null? No, it's not, so that holds true. And my current data is now 11. 11 is not equal to 13, so both conditions hold true. So I'm going to go inside this while loop, and I'm going to shift things again. So my previous is now equal to the current. Current is 0x222. And my current is equal to whatever is sitting inside current next. So it's going to go to 0x333. Okay? So that means in my diagram, my current has now shifted 1 over, and my previous has now shifted 1 over as well. Okay? I'm going to go back and check the condition of my while loop. My current is still not equal to null because it's got a value. My current data is now 13. So is 13 not equal to 13? So that's no longer true, which means I exit out of this loop. Now, when I exit out of this loop, I don't really know for which condition it exited. Did it exit because current is equal to null, or did it exit because my value is equal to the node that I want to delete? So I'm testing why it exited out of it. So first of all, I'm going to check, is current equal to null? No, it's not, which means that this is not the reason why it exited out. So I'm going to go to my else if, and I'm going to check if my current data, so if 13 is equal to the value that I want to delete, which in this case, it is true. Shh. And that means I'm going to go inside this if statement. Okay, so what I want to be doing is I want to be bypassing this current node because it's the node that I want to free and delete now. So what I'm going to do is whatever's inside previous next, I want to be pointing it to whatever is sitting inside current next, because that's how I skip a node, okay? And that's what I've done here. So my previous next is now pointing to current next. And then what I'm going to do is I'm going to delete this current node because I no longer want it. And my new linked list now no longer even considers it. And then at the end, I'm going to return the head of the list. which is what's going to give me, you know, just in case that head has been changed. Okay, all right, how are we going for time? Okay, 10 more minutes to go. How are we feeling about deleting the list, the nodes? Yeah.
So with the previous next equals current next, isn't previous next current?
Okay, so what is happening is that in here, okay, my previous next in here is set to 0x333, and my current next here is set to 0x. Okay, that's not really good writing. Let me just do that, and let me do that. And I'll change the color so it's more obvious. Okay, so this one is 0x333, which is where the next one, this one is 0x444. So what I'm doing is I want this node over here to point to whatever this one is, which is what's inside current next. Because I want to be deleting the current. Yeah. Shh. Say it again. Sorry, I didn't hear the first one. You mean if I haven't used like the previous? So my previous is actually just a variable. I haven't mallocked any memory for it.
It's on the stack, so
But it's going to clean itself up after it exits the function. Okay, so that's what I was saying. We're playing with very little things. Things will clean themselves up, but it's very bad practice to rely on that. You want to be freeing things. But in this case as well, this one, because it's a variable, it's not a dynamic piece of memory. Any other questions about deleting? Tom, can you run a poll? I don't know why I'm yelling at Tom now. Tom's online. Tom can hear me. Thank you, Tom. And what about in the theatre? How are we feeling about deleting nodes? Okay, a bit of thumbs up. Thumbs up, thumbs up, thumbs up. Oh, amazing. Okay, quite a few thumbs up. Yes, when you're inserting into a linked list or deleting from a linked list, it is really important to consider all the boundary cases. So what happens if you're doing something at the head? What happens if you're doing something at the tail? It might not actually change anything the way you write your code, but you need to think about it to make sure that you code for the fact that it might change something or not change something. All right, we're going to finish there for today. And don't forget, Monday there is no lecture. It is the Easter long weekend. I hope you all have a nice 4-day break. And I'll see you next week on Thursday when we'll talk about the exam.